Right, in this video we're going to be having a look at what the photon is. So a photon of light, you must have heard of it before, but I'm going to try and explain it nice and simply for you. So if you have a torch and you turn the torch on like this, we know there's light, and light is projected, it travels in straight lines, so it might get projected onto a screen over here. So what we're going to do is we're going to actually magnify into what's actually happening inside the light itself. So light is made of individual photons, and if you were to draw a photon, the photon would look something like this. So you've got a photon and you've got this bit in the middle. This bit here in the middle is the wave, and the bit on the outside is the particle bit. So this here is a wave particle duality photon. So wave particle duality photon. So what does this statement mean? Well, this statement here means that the photon itself displays behaviors of both a wave and a particle. So you can actually apply both sort of models to the photon itself. So let's just really quickly have a look at how we calculate the energy of a photon. So the energy of a photon is actually given by E equals hf, where h is Planck's constant, and it's 6.63 times by 10 to the minus 34 joule seconds, and f is the frequency of the incoming source of light, and E is the energy in joules. This is in hertz. So that's what we have at the moment. Right, so we've got a question at the moment. Light of a certain source has a wavelength of 400 nanometers. Calculate the energy of a photon of light at this wavelength. So what we do is we're going to use the wave speed equation to begin with. So we know that the wave speed is c is equal to lambda f. So c at this point is 3 times by 10 to the 8 meters per second. That's the speed of light. We know the wavelength of it, and we're after the frequency. So we're going to rearrange this. We're going to say c divided by lambda is going to give us f. So if we put our numbers in, it's 3 times by 10 to the 8 divided by 400 times by 10 to the minus 9. So 400 nanometers is on sort of the blue end of the spectrum and not the red end. The red end is about 700 nanometers, thereabouts. So we do that. By doing this calculation, we get an answer of 7.5 times by 10 to the 14 hertz. And now what we can do is we can work out the energy of each photon. So what we do is we just do 6.63 times by 10 to the minus 34 times by 7.5 times by 10 to the 14. Right, we get an answer of 4.97 times by 10 to the minus 19 joules. If you divide that by 1.6 times by 10 to the minus 19, you get an answer of 3.1 electron volts. So that's your answer in electron volts and joules. We always actually use joules in all sort of in most calculations. Sometimes some people do prefer to work in electron volts. My personal preference is actually working in joules, and there's absolutely nothing wrong with that.